হ্যালো।
ঠিক আছে, একবারে তো।
হ্যালো, হ্যালো, হ্যালো।
আচ্ছা,
হ্যালো।
এখন এটা করতে হবে।
হ্যালো।
হ্যালো।
পূর্ণদি শুনতে পাচ্ছি, পূর্ণদি হ্যালো বলছি ওখান থেকে।
হ্যাঁ, শোনা যাচ্ছে।
হ্যাঁ, ঠিক আছে। ওকে।
অলরাইট, এবার ভূপেন্দ্রটা না, ভূপেন্দ্র তো পরে করবে, একটা গ্যাপ আছে, সেই সময় সেট করে নেওয়া যায়। 10 মিনিটের গ্যাপ আছে না মাঝখানে একটা। প্রথমে প্রথমে 5 মিনিট, তারপরে আমাকে লাগছে তো হচ্ছে তারপরে ওম স্যার, তারপরে টি ব্রেক, পরে ভূপেন্দ্র, আর তারপরে লাস্টে আবার ওই ভালো ওই লিঙ্কটা ডাউনলোড করে দিয়ে করা আছে, লিঙ্কটা উপরে যাচ্ছে, একবার চেক করা আছে, আমি চেক করে নিচ্ছি কোর্স ডান কোর্স। হ্যাঁ, তিনটে অত ওয়াইড হয়ে যাবে, ওর চলে যাবে একটা চাও, তিনটে পরে চলে যাবে, পাঠিয়ে রেখে দিই। পাঠিয়ে দাও।
হ্যালো।
Lot of COVID in the US. So good idea to wear masks. And apparently it's pretty bad. It's like 7 days, young people, 7 days completely wiped out in bed. So
Okay. Good afternoon, everyone. I am Ashna, a second-year doctoral student at the Center for Quantum Engineering Research and Education, and your host for today. Firstly, happy World Quantum Day to all of you, albeit belated. So today we have gathered here to celebrate the World Quantum Day, which is observed on the 14th of April every year, starting from the year 2022. So you might ask what's special about 14th April. Well, the significance of choosing 14th April for celebrating the World Quantum Day is to realize the fact that 14th April or 4.14 is the value of Planck's constant, which is a fundamental constant in the field of quantum mechanics, the theory that underlies quantum computing. So today we have gathered here to listen to various talks, discussions, as well as have a lab tour so that we understand the history and development of quantum computing. So without any further delay, let us kickstart this program. I would now request Professor Bhanu Pratap Das, who is the Director of Secure, to give his inaugural speech.
Thank you, Ashna. So this is actually a welcome address. So let me begin by welcoming all of you to this special event. It's my privilege to give this this address. As Ashna mentioned, 14th April is the World Quantum Day. It's also, Poila Boishak, which is New Year's Day, and it's also the Ambedkar Jayanti. So it's it has significance in many different ways. But the reason why we are gathered here is to celebrate the World Quantum Day. We could not do it on 14th April because it was a Sunday, and as it so happened, the 23rd seemed to be the most convenient day, and that's why we decided to have it on 23rd. Hopefully, in the years to come, we can have it on 14th. Now, again, as Ashna said, 14th April 2022 was the first celebration of the World Quantum Day. Well, the origins are not entirely clear to me, but as if you think, you'll probably realize that by 2020, 2021, it was evident to people all over the world that quantum mechanics is not just an abstract theory, but it has a wide range of applications, particularly quantum computing. 2019 was the year when quantum supremacy was first achieved. That means when a quantum computer could outperform a classical computer. So it was in such a background that people felt that it's important to have a celebration for quantum mechanics internationally. And the World Quantum Day is set up for 14th April, as Ashna mentioned, and she also gave the reason why 14th April. So they formed a World Quantum Day Coordination Committee, an international committee. And there were two members from India, and one of them, I can very proudly say, is Professor Arun Pati. So he represents India in the World Quantum Day International Committee. So he's also our first speaker today. Now, just a few words about our center. We are dedicated to quantum science and technology, primarily to quantum computing communication, and quantum sensing. And it's both research and education. And we offer a few basic courses, but in the years to come, we will be offering many more courses. And so with these few words, I now request Rector, the director of TCC Crest, Mr. Shopan Bhattacharya, to give the inaugural address of this event.
Thank you. I have a speaker here. So warm welcome to you all. Looks like mainly students from which universities were gathered here? Okay. We're hoping to get some more people are coming in small groups. So as Bhanuda mentioned, the World Quantum Day is a significant milestone every year, and I think the significance grows in quantum leaps, one can say. And it is a day when we try to make people aware and understand about the high potential and applications that quantum computing can bring in the future. So I wanted to just cover a little bit about what's happening in the world in the quantum domain, and also to point out some of the things that we hear in CREST and the Quantum Center, which is called Secure, the kind of work that we are doing, and our focus of how to tackle this formidable frontier of science. And as you know that there's a global quantum revolution which is really underway, and its clearest manifestations are in, as he mentioned, quantum computing, quantum communications, quantum sensing. And this is happening all across the world. And so there have been some advances that have happened in US, Europe, Asia in recent years. So 3 quantum computers in the last 5 years have performed computations many times faster than classical counterparts. Efforts are underway in many countries to achieve this type of quantum advantage for a wide range of basic science and real-world problems. The scope of the applications is being progressively widened as well, and it now includes simulations of materials for practical applications and even drug discovery. And this is just a start. It obviously will permeate into many different segments in the future. So in the quantum communication area, there's been a lot of advancements since 2016. Many countries are now trying to establish active programs in these areas. And given that there's been an unprecedented level of security against hacking, so hacking is a major problem across the world. Interestingly, the most recent achievement in this field has been in quantum communications, is between Russia and China. They have a quantum system covering a distance of 3,800 kilometers using secure keys transmitted by China's quantum satellite. So this has opened opportunities for developing both national and international quantum communication networks. It's a little interesting that China and Russia are known to be the biggest hackers in the world. So obviously with the advancement of quantum technology, they are getting better at hacking also. Quantum sensors, of course, measure time, detect magnetic and gravitational fields, and perform many other tasks with much higher sensitivity than traditional counterparts, and have a wide range of applications in our daily life. So the quantum sensors touch us more closely than some of the other aspects of quantum. So active research being carried out in quantum sensing by academia and industries in many countries. And the progress has been impressive and more is expected in years to come. Also recently, you may have come across the incident of Microsoft working with a company called Quantinuum, have actually been able to run quantum computing up to about 14,000 steps, and it has worked with the use of physical qubits and logical qubits, and by combination of quantum and classical, and that has been a major success. So about 4 qubits were deployed to do that, and I think the error tolerance has been really built up nicely. So in their experiment, they claim that you can do 100,000 quantum calculations without any error, which, as we know, are the big challenge that we are facing in terms of fault tolerance. So the Center for Quantum Engineering Research and Education, which is in short form we call it SECURE, it was established in 2020 and is dedicated to pursuing cutting-edge research in areas in frontier of quantum science and technology. And it includes all the various aspects of quantum computing, communications, sensing. We have assembled a team of really internationally trained, illustrious faculty who are going to speak later today. And I think we distinguish ourselves largely from the quality of our people, from the work that we have carried out at this point, mainly in the theoretical domain, but also the application of quantum that we have created, which hopefully you'll get a chance to tour, where we have also developed a lot of hardware and put it in place. So compared to other such initiatives, I think we are among the top few in terms of the quantum domain and how we have been able to build the team, do some recent work that resulted in publications, as well as now we'll use qubits and quantum gates, and we'll be able to solve any problem in principle. The second, which is the quantum annealer, will be made only from qubits and will specialize in solving optimization problems. Both quantum computers will be able to address and find solutions to a large number of scientific and real-world problems. SECURE is the only institution that in India that possesses both kinds of quantum computers. So we have developed over the period with a number of collaborations that I'll talk about, state-of-the-art quantum algorithms to calculate important properties of atoms and molecules using different computing platforms. It was made possible by an award we got from the Ministry of Electronics and IT, MIT as we call it in short. The results of the computations have been published in several leading international physics journals and presented in several prestigious international conferences. The work of these scientists on relativistic and many electron effects in atoms is the first of its kind at the international level. Work in quantum communication is just getting off track, but scientists in this area have very strong track records of performing outstanding research in this area, and important results from scientists are expected soon. Experimentalists from Secure in quantum sensing are gearing up to construct state-of-the-art sensors using photonic, nitrogen vacancy, and cold atom platforms. These sensors will find application in a variety of ways that will affect our daily lives. With certain variations, they could also be used for performing experiments to test fundamental principles of different areas of science. So it is a very important area in the quantum domain. So we have also been working to provide support to the National Quantum Mission that you must all know have been put in place by a cabinet, government of India. So basically the government of India is supporting development of various aspects of quantum technology, and they have created a very detailed call for proposals that cover all the important areas of quantum technology and computers. And we have been one of the key technical groups who have applied for several of those potential applications. And but we are awaiting the result of their evaluation of the proposals. It's probably going to take some time, but working with them will allow us to really, take a leap in terms of how we take the quantum area forward. So CREST and Secure has built very strong collaborations with groups of many leading institutes and universities in Japan, US, Spain, UK, and Germany, as well as national groups including several IITs, national laboratories, universities, and high-tech companies like IBM. Secure has received national and international research grants, including a grant from European Innovation Council through its collaboration with Kilimanjaro, which is a quantum technology company in Spain. Last but not least, we have a very strong PhD program, which is unique in some ways. It offers courses encompassing all the important aspects of quantum computing, communications, and sensing. Currently, we have 13 PhD students, including a foreign student from Cameroon. CREST is also looking to develop a deemed to be university, which will expand the student pool. And also we intend to introduce high impact MTech, MSc type of programs. So our expectation is that maybe from next year we would be able to inaugurate this university, and that will really open us up to ability to bring in much more collaboration with the younger people, and also bringing in much more number of students, both for PhD as well as MS level. So thank you very much. I hope you have a productive day today in terms of what we have put together in terms of content of today's program. And Bhanuda, who's next?
Thank you, Professor. We shall now begin our series of talks. The first speaker is Professor Arun Pati. He is well renowned in the field of quantum information and quantum computing. So
You can take this one.
Okay, no? Okay, so good afternoon, everyone, and happy World Quantum Day to all of you. Uh, so, in this talk, what I plan is I will try to give a historical account of quantum mechanics, how it was developed, starting from old quantum theory. Then slowly I will go over to the new quantum theory, and then towards last part of my talk, I will try to talk about computing, quantum technology, and what currently all over the world, people are trying to do. So this is kind of plan I have today. So, all of you know that quantum mechanics has really a different kind of theory which is so counterintuitive to the classical world that you are familiar with. The world that you live in, the world you see around yourself is something completely different than the quantum world where these subatomic particles they behave and all the dynamics happens. So quantum mechanics is one of the finest theory. This point is not working or okay, very small. And it is the basis of all modern science or modern physics that explains the nature of different systems and behavior of matter and energy on the atomic and subatomic level. So as I said, I will briefly touch about old quantum theory, then go over to new quantum theory, and slowly I will discuss about few things in quantum computing and quantum technology. So I'm not going to go into my detail, but just to for students so that you feel at home, don't feel out of place. So I will spend some time that already things you're familiar with. So quantum theory already is quite old, about already more than 124 years, around 124 years old now. So it all started with the father of quantum mechanics, that is Max Planck, and he tried to explain this black body radiation in 1900. And when he entered physics, one of his teachers, if you don't know the name, he told to Planck, physics is finished, young man. It is a dead end street. Okay, so it was so demotivating for Planck. Okay, so but nevertheless, he did not give up, and he pursued his own interest. And even his PhD advisor told that in this field, almost everything is already discovered, and all that remains is to fill a few holes. It is still, further demotivating, for a young person like Planck. But Planck was something, somewhat different. He did not wish to discover new things, but only to understand the known fundamentals of the field. So with that motivation, he started out, and he went on to explain this black body radiation. And classical physics, as all of you know, was not able to explain this this phenomena using classical physics that are known at the time. So Planck resolved this issue by postulating the thing that black body can be thought of as a collection of oscillators which exchange energy in discrete unit proportional to the frequency of the oscillator, which is the famous quantum equation you see, that E equal to h nu. And with that simple hypothesis of simple postulate, he could explain the whole black body radiation. And that is now history and starting point of the quantum mechanics. And then, sorry, wait, so yeah, so at that time, Planck considered this hypothesis only a mathematical artifact. He did not give too much emphasis, or physical meaning to this hypothesis. He thought that this is purely a formal assumption. Actually, I did not think much about it, because at that time this was going against all the classical notion of physics, and this is regarded as the birth of quantum mechanics, and in fact the greatest intellectual accomplishment of Planck. So that is really remarkable. So then came Albert Einstein, whom you already know. He took another step in trying to explain this photoelectric effect, which was discovered by Hertz and Thomson. And he postulated that if you regard this light not as a wave, but a discrete unit consisting of single entities like photon, you could explain this photoelectric effect. And this is your familiar, most famous equation that Einstein proposed. And using that, he could explain the photoelectric effect. And again, he used this Planck's notion that E equal to h nu. Then came Bohr. All of you are familiar with this. So Bohr was trying to explain so-called energy levels of the atom, and he could assume few of these things, which later on actually could derive using Schrodinger equation, but at that time it was kind of postulate, so often you call them Bohr's postulate. Using these kind of postulates, the electron revolve only in certain orbit without emission of energy, and they go around nucleus only in unit of this h bar, nh bar, and when they make transition from higher to lower orbit, they emit a single photon with energy equal to energy of the difference between the two levels. With these three postulates, you could explain the spectrum you observed in the atom. Then came Louis de Broglie, but before that, there was a long thread of thoughts after Einstein's work. So, because with Einstein's proposal that photons consist of discrete unit of energy carrying objects like photons. So he said that there are now two theories of light, both indistinguishable and without any logical connection, because one is regarded as a wave, which is a continuous phenomena, and other is a discrete entity, which is nothing to do with the wave nature of the light. But nevertheless, that suggests that there is these two entities which you need to explain different phenomena. So, like evidence of wave nature, you need to explain diffraction and interference. You need the particle nature of light to explain the photoelectric effect, Compton effect, and so on. So, light, if you regard it as a packet of discrete entity like photon, then you can explain this effect, and you can explain, as I said, other effect like diffraction and interference using wave nature. You never find photon as half of a single photon. You only see either wave nature or the particle nature. So this these notions was so crucial at the time, or so perplexing at the time, that Louis de Broglie thought, why not? How to do with only photon? Why not the other elementary entities? So he thought, okay, so if photon can behave like both wave and particle, why not an electron, or why not other particles, or even matter? So he said, okay, so let us propose that not only light, but all the elementary entities, they should behave both like wave and particle. That's how what is called dual nature. So in particular, he said electrons should not be considered simply particles, but that frequency should be assigned or must be assigned to electron also. This is the quote from his Nobel speech in 1929. And if that is so, then you should see the consequence of this hypothesis or this postulate, and that is you should see diffraction pattern or interference pattern with a matter wave. Does it happen? Yes, indeed, that happens. So immediately, 2 years later, people did experiment and verified this hypothesis or this postulate. So de Broglie proposed that all the particles with some momentum p should be associated in wavelength, which is given by this famous equation that you are familiar. And this wavelength of a entity like electron depends on the momentum, not on the size of the physical particle. And in 1927, these people, Davidson and Vermeer, they did actual experiment, and they actually tested this diffraction pattern using this Bragg's condition. And this is the first experimental evidence that indeed electron behave like wave. And also, if you do the interference experiment with the double slit setup with quantum entities, you do see interference. I will come back to this little later. So So in one hand, you had classical mechanics. On the other hand, quantum mechanics was slowly developing from 1900 to 1920. So still, scientists at that time, they're not very clear what is really going on. So is it true that quantum mechanics is some higher theory and classical mechanics is a limiting case of quantum mechanics? So what is the connection, what is the correspondence, and so on? So Bohr came in 1920. He said there must be a correspondence principle. That is how you get classical mechanics from quantum mechanics. So he thought that maybe one should tell some, guidelines, set up some rules, because already it was highly successful in describing microscopic objects or microscopic phenomena at the time. And we know that also macroscopic system obeys classical mechanics. So if quantum mechanics is applicable to macroscopic object, there must be some link with this quantum mechanics, which reduces to classical mechanics in some limiting case. So he said, so quantum and classical physics should agree when quantum numbers described within system are very large. Limit of large quantum number, one should be a limiting case of the other one. Okay, so after 1920, slowly various things were happening. Again, not going into too much detail, but I will try to tell little bit about new quantum theory, 1926, how Schrodinger equation was developed and interference of single particle, then Heisenberg uncertainty principle, then probability interpretation of the wave function, then quantum measurement, and Dirac developed his equation for electric electron, quantum entanglement, and then slowly I will come to this modern topic of quantum computing and quantum information science. Okay, so Schrodinger equation, already all of you are familiar. And this equation answers this question, that how does the matter wave evolve in time? And why this question comes into mind? Because de Broglie already told at the time, that 1924, that already every entity should be associated with a wave. So if that is so, what is the equation governing the wave? Okay. So Schrodinger came up with this equation, which tells you that if the particle is moving in some potential V of x, and it has some kinetic energy, say classical, which is given by p square by 2m, then the total energy is essentially kinetic plus potential energy. And then the kinetic energy and potential energy, if you add up, that is total energy, that acting on some wave function psi should be given by this IH bar del psi by del t. And the equation that you all familiar, and one of the most remarkable equation in physics, because whole of modern science is based on this single equation. And this equation came to his mind out of blue, there's no derivation, no proof. So he just somehow got this idea, and he wrote down this equation, and he worked out some example, and he worked, and he's still working, and he will continue to work till the whole universe exists, continue to exist. So this is the beauty of Schrodinger equation. So this wave function satisfies this equation, and this is one of the most fundamental equation that you see in quantum mechanics. And the most mysterious thing in quantum world, which is to do with quantum interference, okay, which I will spend a few minutes. So think of a wall with two holes, and there is a source, and suppose the source is firing bullets one by one. Okay, if this hole is closed, I don't know, this point is not visual somehow. So if this hole is closed and the bullet is coming one by one through this hole, you will see, you will see this kind of hump if you wait long enough. If you close this one and this is open, you will see a hump which will look like this. And if you open both the hole and wait long enough, the distribution you will see essentially sum of these two, which is something like this. So this is what happens with classical particles. Okay, but suppose you do the same thing with quantum particles, what will happen? So suppose there is a source which emits electron one by one, or which emits photon one by one, and you have a two slit open. So this is the typical Young's double slit experiment. So again, imagine same situation. So you close one slit, open one, and if you wait long enough, you will see a distribution something like this. If you close this one and keep this open, you will see a distribution something like this, exactly like classical. But if you keep both the slit open, you don't see something like this. You see a pattern which something like this, which is essentially not the sum of these two harms or to this distribution, but something else. That something else is essentially to do with quantum interference, and that is to do with the fact that the wave function of this entity has amplitude of going through slit 1 and slit 2. And this distribution is not just the sum of these two distributions, but essentially you add up the amplitude, then take the square of that. Because of that, you get a cross term, and that cross term explains the quantum interference. So I think this is the same thing I said. Oh, no. Yeah, so what I want to point out here is the following, that what I said is the standard double slit setup. But now suppose you put a detector behind the slit. Okay, suppose you put a detector here. You want to monitor through which slit the particle is going. Okay, if you do that, then even if it is open, you will see a hump like this. If you put a detector here and this is open, then you will see a hump like this. That means the interference pattern completely washed out. So by looking at the particle and monitoring through which slit it is going through, you wash out the interference. So this is this so-called quantum measurement phenomena, which I will come back a little later. But essentially, the whole mystery of quantum mechanics is to do with this quantum interference. So electron, we know behave like wave. You have to introduce two amplitude for the electron going through slit 1 and slit 2. When both slit 1 and 2 are open and no measurement is made, the resultant distribution is square of the modulus of the sum of the amplitudes. And probability amplitude obey the superposition principle when different paths are not known. But if you know which path electron passes through, the electron exhibits like a particle behavior. Not knowing which slit electron goes through, the electron exhibits wave-like behavior. So essentially, if you put detector behind the screen, you monitor the path, you lose the wave nature. If you don't put the detector, you retain the wave nature. So it also tells you that the single entity, electron or photon, whatever you are sending through this double slit, each of those entities, they pass through both the slit. Because if you don't assume that, you will not be able to explain the interference. You need that. But if you ask the question, how does the single electron go through both the slit? Nobody knows. Okay. So this is the whole mystery of quantum interference, quantum mechanics. Okay. You still don't know. Maybe in future you will get some answer, but still you don't know the answer to this question. And here is the famous quotation from Richard Feynman. So he refers to this quantum interference. This is a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. So the mystery still continues. Okay. So if you are interested, you can think over this question, but I don't know whether you will get the answer. So the interpretation in quantum mechanics that you see in your standard textbook, that had to do with so-called this Copenhagen interpretation. And this was developed again around same time, between 1926 to 1930. So because this theory was so counterintuitive, so different than classical mechanics, people are not able to really appreciate what is going on. So because sometimes you behave like a particle, sometimes you behave like a wave. So which is it? So Niels Bohr would say that when you treat like a particle, it is a particle. When you treat like a wave, it is a wave. And it is meaningless to ascribe any property or even existence to anything that has not been measured. So nothing is real unless it is observed. So this is very deeply philosophical, but it has a lot of application in quantum information, quantum communication, and so on. So then comes the famous uncertainty relation due to Heisenberg. In classical world, we know that given any particle moving in 3D space, you can precisely measure position and momentum. And accuracy of your measurement depends on the quality of your measuring device. But in quantum world, this is not so. Even if you have a very sophisticated device or very, highly resolving instrument, still it will be impossible for you to measure certain observables. For example, if you want to measure position and momentum, you cannot measure both with arbitrary precision. So more precisely you know one property, the other is less precisely known. And this is the so-called famous Heisenberg relation that delta X delta P is bounded by h by 4 pi. This already all of you know. Now I will make a little diversion from for a few seconds. So can there be any uncertain relation beyond Heisenberg? That is, can you prove something better than Heisenberg so that this particular relation will be a special case of this more general relation? And this question was there in my mind when I was doing MSc, and we proved a new relation in 2014, and that is stronger than the Heisenberg relation. And I'm not going to again to detail, but just to motivate young students. So you see, what you learn in your textbook is not the end of the story. Okay, you have to keep asking questions. Some questions are necessity, some questions are curiosity driven. Okay, so not every question has to be driven by your necessity. Something you have to ask out of curiosity, and maybe you can pursue, and maybe one day you will find the answer. And particularly the stronger uncertainty relation that we proved in 2014 along with one of my collaborators from Italy. This had to do with something I started thinking in 1985 when I was doing my MSc. And it is just out of curiosity. I thought, okay, is it this whole story or there's something else? Can I prove some better relation than Heisenberg, which will be a special case of my new relation? So I was thinking, but no progress. But one day it happened, and that was the result in 2014. And you could show that this Heisenberg relation is a special case of this, and this has a lot of application in quantum technology, starting from quantum metrology to quantum entanglement and quantum computing and many more things. Okay, so that is a different story. So that to explain that, you need another set of lectures. Okay. So coming back to the meaning of uncertain relation, why it is so fundamental? Because that changes the whole worldview. So classically, what you are thinking, what you are trained to think before 1927, and what you think now or after 1927 is completely different. Because every concept has a meaning only in terms of the experiments used to measure it. Things that cannot be measured really have no meaning in physics. So in particular, path of a particle has no meaning beyond the precision with which you can measure it. In classical physics, since Newton, we know that the real world exists independent of the observation or independent of the observer, regardless of whether or not we observe it. Okay, and this has again very deep and profound implication in quantum science and quantum communication. What it tells you is the following: that in classical world, whatever you see, suppose this pointer has a color white. Okay, this is independent of my observation or your observation. Okay, but in quantum mechanics, if you attribute a property to a physical system like this color of this pointer is white will depend whether you look at it or you look at it. Okay, so this is not something independent of the observer. Okay, that is the meaning of, in simple terms, that is the meaning of this statement. So in Heisenberg argued that such concepts as orbit of electron do not exist in nature unless and until we observe them. And this is the famous quote from his original paper. I believe that the existence of a classical path can be formulated as follows. The path comes into existence only when we observe it. And then came your Born's interpretation of wave function, which all of you know. And for this, he got the Nobel Prize. Again, I'm skipping this because all of you know this. And there is something intricate about quantum mechanics, that is quantum measurement. So unlike classical system, everything is so determined, so perfect, and when you do measurement of some classical system, nothing happens to the system. Okay, but this is not so in quantum mechanics. If you have a state of a system, then you have to associate some wave function, and you know that if you measure some physical quantity, then you will get one of the answer, and that answer will be a real number, which is essentially the eigenvalue of the observable that you are trying to measure. And the measurement outcome is not predictable. If you are measuring some physical quantity, you are not sure whether you will get this eigenvalue or that eigenvalue. That is completely random. Okay, and that is essentially probabilistic. And once you do a measurement that causes disturbance to the system, which cannot be removed at any cost. That is to say that you may think that, oh, maybe I will design a suitable, very sophisticated instrument which will measure the system without disturbing it. No, it's not so. You cannot do that. Once you do that, the function undergoes a collapse. And this collapse is actually an irreversible process. That is, you cannot recover the original function of the measurement. And all these, again, you need to make connection to the experimental, observation to explain the experimental results in your lab. But if you ask the question, how does collapse occur? That is still not solved. And this is still an open question in quantum mechanics for last 100 years. Okay, so then there is notion of quantum entanglement, came in 1935. Again, this is an active area of research in quantum computing quantum information. There's a lot of development has happened over the last 20 years or so, but this notion was already there in 1935. But it tells you the following, that if you have two or more particles, you can create entangled state through some interaction. And once you entangle them, one particle cannot be fully described without considering the other object. So to describe this entity, you need this single wave function. Okay, that is an entangled state. Typical example could be that you can have entanglement when subatomic particles decay into other particles, and the decay event over the various conservation laws, and as a result, pairs can be entangled in quantum states. And if two particles are entangled, then they are strongly correlated, as if they are two lovers. And that means if you know the state of one particle, you know the state of the other particle, even if they are far apart. This is exactly like what happens if you have two lovers. If one person is living in Delhi, other is in Bombay or Calcutta, they feel strongly correlated, and they may be in same state. So here are some famous quotes from Bohr and Feynman, that anyone who has not been struck by quantum physics has not understood it. The word quantum refers to this peculiar aspect of nature that goes against. And all these debates are going on in around this time, this Solvay conference. Most of these, interpretation and meaning to quantum mechanics actually happened in this conference. So if you ask what are the applications of quantum mechanics or quantum theory, and there are tremendous applications over the last 100 years or so. And quantum mechanics developed by Heisenberg, Schrodinger, and others changed the worldview and gave a glimpse into the nature of reality at a macroscopic level. Quantum theory also helped to develop relativity equation for electron by Paul Dirac. And all the modern science starting from nuclear physics, particle physics, solid state physics, what you call now as condensation matter physics, or even string theory, and almost all area of modern science are actually the basis is pure quantum mechanics. Okay, without quantum mechanics, you cannot make any progress with all this. And quantum mechanics is also essential for modern technology, including various electronics items that already you are using. So now I come to quantum computing part. So again, briefly, I will tell you the recent developments or the innovations in quantum computing, quantum communication, quantum measurement and metrology. I don't know if you have time for this, and a few things in quantum information processing. Okay, so before I tell you about quantum computing notion, let me tell you about classical information. Already we have seen a IT revolution in information technology. So present-day computers, or in fact all the devices that you use, they store information only on transistors switching between on and off state. And you can say you can store two different state like 0 or 1, which are two possible state of a classical bit. And then you can perform various tasks according to classical laws of physics. When I say classical laws of physics, it can be Newton's law, it can be Maxwell's equation, or anything you can think of. But you never find your classical bit in combination of the logical state, only either 0 or 1. There was an initial early motivation due to Moore's law, that is the basic rule which states that number of transistors on a chip doubles every 24 months. And that has been guiding principle for all the high-tech industry since it was coined by Intel co-founder Gordon Moore in 1965. So for example, if you go back a decade ago, you could see that companies are building chips at this 500 nanometer level, and now various companies are trying to solve engineering problem and trying to make chips even smaller scales. So this is a kind of empirical plot which shows that by 2030 you need transistors which will be about 2 nanometers in size. That means you will reach a scale which is 4 atomic distance. And we know that at this atomic scale, classical physics breaks down, and you have to use quantum mechanics to store and process information. But this is not the only motivation, but initially people thought this is one of the motivation. But there is a bigger motivation due to Richard Feynman. I will come a little, in few seconds. But before that, I should tell you that how physics and information are connected. Before 1980s, people were thinking that information science and physics, they are completely different subjects. Because information science is something abstract, something mathematical. Physics is something to do with real, concrete, physical system, physical examples. But it was a great insight by Ralph Landover, who is again one of the great classical computer scientists. He realized that any information processing is actually a physical phenomenon happening in a physical system. Okay, and this point of view actually led to the notion of physics of information, and that actually led to the notion of reversible computing. And Charles Bennett, who is one of the founding father of quantum information, that helped him to do many things in quantum computing. So, and all of we will agree that physics is deeply involved in fundamental work, which ultimately leads to various technological developments. You can cite many examples starting from computer to internet, electronic devices, and recently this emerging technology, so-called quantum technology, quantum computing, quantum communication, and many more things. Okay, so the bigger motivation for quantum computing actually came due to Richard Feynman in 1982. he realized at the time that if you want to simulate complex quantum systems on a classical computer, you will not be able to do that. So this classical computers will be very, very inefficient in trying to simulate a complex quantum system. So then he asked this question: what can happen if you store information in these two distinct states of a quantum object? But then he left this question open at the time, so without much progress. But in 1985, David Doyce, who is a British physicist, he took this idea further and he realized that if you use quantum mechanical superposition principle, that can allow a new way of storing information in quantum state. And then he developed the whole theory of quantum computing, starting from this notion. So quantum computer essentially, in simpler terms, a device that performs computation using principles of quantum mechanics, the ultimate theory of nature. So this is the view that David Doyce tried to put forth, and he developed the whole theory of quantum computing. So how to store information in quantum state? So think of a single photon and identify two states, like say horizontal polarization or vertical polarization. Then if it is H, you say it is. If it is V, you say it is 1. But then you know that quantum mechanics allows linear superposition of two distinct states. Okay, that means you can have a state which is alpha 0, alpha H plus beta V. Okay, so once you have this kind of state, which is allowed in quantum mechanics, what you have is essentially H is 0 and V is 1, so we have a state which is alpha 0 plus beta 1. And that is essentially a new kind of notion that you don't see in classical world, and that is essentially a quantum bit, or in short you call a qubit. So why is it different than classical bit? Because in the classical world, your single bit can remain only in one state at a time. That is either 0 or 1. Okay, but this quantum bit can remain at the same time both this and this. Okay, so that is the remarkable difference you see when you go to quantum mechanics, and that you can realize this kind of state. And that also happens with the latent spin. You can encode a spin, spin up equals 0, spin down equals, you say it is 1. Then you can have a state like alpha up plus beta down, which is alpha 0 plus beta 1. And you can think of any state. You can think of a ground state as 0, as 1, and so on. And then you can create a quantum bit or qubit again for a single atom also. So the key difference or key thing that you see is that your classical bit somehow able to parallelly assess both the logical state 0 and 1 at the same time. Okay, and that inherent parallelism is responsible for new type of computing, and that's what is to do with quantum computing. And here is schematic view, so you can store in up and down state, and also you can store in alpha up and beta down state, which is essentially a quantum bit. And if you now think of a collection of quantum bit, you can design a quantum register. So think of a 2-bit register. You can think like 0 0 0 1 1 0 1 1, and again you can think of like up 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 down and down up and down down. But then you know that you can have a combination of all these, that is alpha or A this plus B this and C and plus D times this one. Okay, so this is essentially general state for a 2 quantum bit. And now if you can think of 10 quantum bit, you can see that you are able to assess all the 2 to the power n possible logical state in one go. So that means you are able to somehow assess the vast exponential number of logical states, because of the linear superposition which is there in quantum mechanics. And quantum entanglement, as I said in the beginning, they provide strong correlation. Even if they are far apart, they are not independent, and this is one of the weirdest features that you see in quantum world that allows you to do amazing tasks which are otherwise impossible. And these entangled states you cannot understand using classical common sense. So again, this was, as I said, coined by Schrodinger, and at the time, he could realize that this is something different than something drastically different than the classical line of thoughts. And Einstein, Podolsky, Rosen, they also use this entangled state, and they try to bring out how this entangled state actually displays Fourier correlation, and essentially they try to use this entangled state to argue against quantum mechanics. That is, because Einstein was not very happy with the way quantum theory was being developed, so he used entangled state to argue that maybe there is some bigger theory, maybe there is some higher theory than quantum mechanics, and quantum mechanics is a special case of this. So that was his motivation, but nevertheless, one of the most remarkable paper, and which has a lot of application in quantum communication. Again, that will take a different direction, so I'm not going to too much detail. So all it tells you that if two qubits are in entangled state, even if they're far apart, they are somehow connected. Okay, so just to highlight what a quantum computer is doing. So classical computer, you have a collection of bits, and those classical bits can be either 0 or 1, but quantum computer can be both 0 and 1. And they assess a exponentially large number of logical states, and they can compute multiple values at once. And quantum computer can exploit this feature like linear superposition, entanglement, and other non-classical features to carry out messy computation in parallel with better speed up compared to the classical counterpart. So over the last several years, various algorithms have been discovered, starting from Dias-Joza to Grover's algorithm, Shor's algorithm. Recently, a lot of interest going on in variational quantum algorithm, adiabatic quantum algorithm, and so on. So essentially, you want to design your quantum computer which can implement certain algorithm and try to give you answer in maybe in shorter time scale, or maybe much more efficiently, much more speed up way, and so on. So that is the bigger goal of quantum computing. And over last 5 to 8 years, there is a global race to build quantum computer. In 2016, IBM built first quantum processor with 5 qubit, and slowly over several years, they've gone to 27, 65, 127, and 433. And very recently, just in November, this company, Atom Computing, they built about 1,000 qubits, and IBM in December last year they built about 1121 number of qubits. So you see the way they are progressing is really tremendous. And quantum computing is only a part of the larger picture. Quantum information is the bigger, bigger topic. Under quantum information, we have quantum computing, quantum communication, quantum metrology, quantum sensing, and many more things happening. So, and why quantum information is interesting? That is to do with also some feature about quantum bits. That is, quantum bits are very private in the sense that to store information in quantum bits, they don't reveal to the other user what you have stored in it. So, for example, suppose I have a quantum bit and I have stored some information in that quantum state. Okay, then if you are coming and trying to read the information or copy the information, you won't be able to do that. Okay, that means quantum information stored in a quantum bit are completely private. Private in the sense that the person who has stored the information, only he or she can read or make copy or manipulate it or tamper with it. Nobody else can do it. Okay, so two things I will just try to highlight, not into my detail again. So classical bit, all of you know, you can copy perfectly, but quantum bit, it so turns out that you cannot make copy. And similarly, classical bit can be deleted from 2 copies, but quantum bit cannot be deleted. And these results often called as no-go theorems, and they have deep implication in quantum computing, quantum communication, and quantum cryptography. So again, not too much detail, but here is a just I will spend 1 second here. So you want to build a device like this, and you want to have a input, and you want to have a blank state, and you want to make 2 identical copies. And this is not again possible and that is very famous result, so-called no cloning theorem. And similarly, you have two identical copies, and you want to build a machine like this, and you want to retain one and then delete one. And again, that is not possible, but classically you can do it. And that is something called a no deleting theorem. So quantum information as a bigger subject, you can ask what is the goal? What is the big goal of this subject? Okay. So the big goal here is how well you can store, process, and transfer the vast amount of information contained in quantum state using principles of quantum theory. So what are the features you want to exploit? You want to exploit features like superposition, like entanglement, non-locality, to do some practical applications and doing amazing things which you cannot do in classical world. So here is a schematic of quantum communication. You have a sender, Alice, and the receiver, Bob. You are connected by a quantum channel, which is typically entangled state. Then Alice can do something and send something over classical channel, and then Bob can do something. At the end, they can share quantum state, they can send classical information, and so on. So this is the typical setting where quantum communication happens. So again, I will. How much time I have? 5 minutes? Yeah, fine. That would be fine. Yes. So there are many things happen over last 20 years or so, but I will just highlight few things. One is quantum teleportation and remote state preparation, quantum secret sharing, quantum cryptography, quantum internet. So in teleportation, essentially is very famous in quantum information science. That had to do with something similar to quantum Star Trek. So you have a sender, Alice, and there is a quantum bit entering her lab, and by doing something, that object will get destroyed and will appear here, and that is again possible using the entangled state shared between Alice and Bob, and by sending two classical bit. So this was proposed in 1993, and the first experiment was done in 1997, but over the last several years, people have done over very long distance also. Okay, this I will skip. This is typical, how a futuristic teleportation will look like. You want to build a device, and you want to enter here, and then press a button and disappear and appear at a distant location. This is now no more a science fiction. This is actually possible with quantum information. And this is the first experiment that people did in Austria, in Innsbruck, in 1997. And there is also called remote state preparation, where the idea is the following: that you have a quantum bit of certain kind in your mind. Unlike teleportation, there is no input, but you have only the classical description of the quantum state, and you want to recreate that at a distance lab. So just to give an analogy for a second, I really like, suppose you want to prepare a dish, some delicious dish at your friend's kitchen. Okay, the way you can do it, you prepare this here and send it by courier, and your friend can open the courier and eat in her kitchen, right? That is one way. Or you make a telephone call and tell, okay, you do this, and she'll prepare there. Okay. So similarly, suppose you have a quantum state and something of your choice, and you want to create same state in a distant lab. How can you do that? Either you prepare the qubit in your lab and pack it and send it by courier. But courier means maybe optical fiber or some channel, and send it to your friend's lab. Or you tell, okay, my state is this, make a telephone call and send a lot of classical communication, and your friend will prepare it. But if you use entangled state, by sending only one classical bit, you can prepare your state at a distant location. That was the idea. And this was schematically looks like this. You have the entangled pair, and you have a person here, and she will send only one classical bit, and then Bob can get the state. Okay, so coming to secret sharing, the idea is the following: that the two person, Alice and Bob, and they want to have a joint account. Neither of them can have access to it, but together they can withdraw some money. That requires a password. A classical example is something like this. Suppose you have a string like this, 011, this string, okay? And Alice has only a string of random number like this, and Bob has a bitwise addition of this and this. So Alice has this, Bob has this, but neither of them they have this key. Okay, but if they come together, they can add, they can do the XOR operation, and they can get the key. Now, over the last several years, people are using this simple idea to using multi-particle entangled state and do secret sharing. That means you want to store some secret information in entangled state so that neither this, nor this will know what is there. But if they come together, they can extract the information. Okay. The last part is about to do the cryptography, where you want to encode something and send it to the person who can get the message that you sent by using some shared key. In classical example, is Caesar cipher or one paired. Similar thing already proposed long back in 1984 by Bennett and Brassard. So Alice and Bob, they want to set a key using this quantum channel. In classical channel, they can do certain operation. Again, I'm not going to more detail. And they can, in the end, they can set a secret key. And this is the typical setting of quantum cryptography, which is widely used nowadays. Also, there is a proposal for quantum internet, where you can store information in local node, and then you can connect the nodes by teleportation channel and transport keys from one side to another side, and you can distribute even entanglement. And in future, maybe you can download a qubit, you can download entanglement, and can use for communication or computation and send it back to the node. So this is also, this kind of ideas are also there. Okay, so the quantum technology, the larger goal is you would like to have a technology that is that has far-fetching innovation based on quantum theory, and that will make your device smaller, faster, and much more powerful than the present day devices. And that can comprise quantum computer, quantum software, quantum internet, telephone, and quantum network, and many more things. And many economic and even private industry that trying to also work on precision of atomic clock, and also trying to design algorithm for tackling hard problems and potential Earth to space quantum key distribution and so on. So once you achieve all this, that will change nearly every aspect of future life. There's no doubt about that. Okay, so I think this I can skip. So just to before I summarize, just to give a glimpse of this interdisciplinary nature of the field, it is not that to do this to do research in quantum computing or quantum information, you need to only know physics. No, you can come from various background. You can come from physics with a quantum theory background. You can be computer science, you can be engineering, or information theory, or communication. So many truly interdisciplinary, you know. So that's the beauty of the subject. Okay, so I am there finally at the end. So I started with the historical background, how quantum theory was developed and how it had deep impact or implication on all of modern science. And also I tried to tell you how quantum information that you store in quantum fundamentally differs from classical information. And this quantum information exploits the principle of superposition and entanglement. And these quantum computers can do certain tasks much faster compared to their classical counterpart. And also I tried to tell you how quantum bits are, they maintain the privacy in the sense that you cannot make and cannot make copy. Sorry, you cannot copy and cannot delete it. So that means information stored is secure at a more fundamental level. And quantum technology allows new way of communication, like teleportation or this remote state preparation or quantum state sharing, quantum cryptography, quantum internet, and many more things. And next revolution you will see, or already we are seeing actually, quantum computing and quantum technology. And that is the main reason why there is a global race to build quantum computer, quantum communication system, quantum sensor, quantum devices, and many more things. Okay. So with that, I'm there. I'm all done. So for young people, here is my thought. So there is no dead end in science. It is left to our imagination and creativity to discover something new. So stay motivated and do something new. Okay. Okay.
Are there any questions from the online audience? Thank you, Professor Pati. We shall now have a 10-minute tea break and then resume for the next talk. Thank you. All the students are requested to have cookies from outside.
না স্যার ল্যাপটপটাই করছি কি হতে পারে
আমি পিপিটি তোমাকে পাঠিয়ে দিই।
হ্যাঁ হ্যাঁ সেটা যে বলতে অ্যাক্সেস হচ্ছে পিপিটিটা খুলতে গেলে গুগল ড্রাইভে অ্যাক্সেস চাই কারণ এটা অন্য একটা ইমেল অ্যাকাউন্ট। হ্যাঁ হ্যাঁ হ্যাঁ
এটা কেটে দাও।
অ্যাক্সেস নাই দুইটা
Leave, ready?
এটা ইউটিউবে কি কোনো মিররিং হচ্ছে এখানে?
মিলারিং
আচ্ছা, মিররিং এর জন্য
এক্সট্রা
স্নেহর একটাকে ওয়েট
আর দেখাচ্ছে রেজলিউশন এখানে একবার কথা বলো করেছো? হ্যাঁ, হয়নি তো মনে হচ্ছে। হ্যাঁ, ঠিক আছে। আমাদের তো ওটা অফ করতে হবে। ঘুরে যাচ্ছে নাকি ওইটা দিকে?
এবার
ঠিক আছে,
হুম
শুনতে পাচ্ছ তুই?
হ্যাঁ
আচ্ছা,
এই তো
ঠিক আছে।
এবার বন্ধ করে দেবো পরে একবার on করে দেবো।
Actually,
Okay, so we shall resume our talk. The next speaker is Professor Bhupendra Nath De. He is well known for his work in experimental condensed matter physics. And he's currently leading his efforts to build a quantum computer here at Secure. So, Professor.
Okay, good afternoon. So you have heard the talk by Professor Poti. He has given you essence of everything that you need for quantum computers. But I'll just use bare minimum of quantum mechanics in pictures. That's the guarantee. Anyway, so the title, The Quantum Computers, an Emergent Revolution. What does the word emergent means? In the process of being or being prominent. And what is revolution? A rapid transformation. It could be political, it could be in science or anywhere, a rapid transformation. So that's what will be the essence of this talk. Okay. Oops. So what is quantum computer? By this time you have already learned. It's a quantum technology that's built using the principles of quantum physics or quantum mechanics. And this has enormous potential, as I call revolution. So just I begin with a glimpse of that, what it is. Professor Bhanudas already mentioned about this. So this is a small quantum computer. It's a 34 qubit, 53 qubit. And they have in 2019, they have already carried out some calculations. They did it in 200 seconds. And they claimed that the present day, the best supercomputer would have taken 10,000 years to carry out the same calculation. That means impossible, right? So that impossible task has been done in 200 seconds. You can see what is waiting for us in the future. So let's, as I said, I'll be talking with pictures. So with the classical versus computer, large versus small, if you throw a ball from here, if you know its initial position and velocity, you can predict exactly where it's going to land, right? But if this ball is not big, if it is small, what happens? Say I have this large ball here. This could be solid or hollow, whatever. Say it's a solid ball. Now you take materials out from here, remove, and finally you go to this atom. Now you are doing the same experiment earlier, throwing this atom, right? Can you predict where it is going to land? For the big ball, I could. For the small ball, you cannot predict. You have already learned some uncertainty principle like delta x, error in x, error in momentum. All these things are there. So then this is governed by quantum mechanics. So now what is said, I can say something. It's not exactly there, but around there somewhere it will land. What you can say that exactly at the center, what is the probability of landing there? That's what I can calculate from quantum mechanics and tell. So it has 50% probability of landing at the middle. And then at surrounding areas, there are certain probabilities there. But if I throw this atom once, I don't know where it's going to end up, right? So my prediction, there's a 50% probability. Any experiment you want to do, with single event, you cannot interpret that. When you throw a coin, you saw that the probability of landing with head is half, probability of landing with tail is half. So it once, any one of them will come. We cannot predict that. If you throw 1,000 times, then you will see about 500 times head will come and about 500 times tail will come. This is you can interpret that. So the quantum things, you have to do that. If you have to carry out an experiment, you have to do the similar experiment many times, 1,000 times, 1,00,000 times, whatever. Then only you can interpret that. So this is one change in the thoughts. Then quantum particles have many strange and unusual properties. Professor Poti has explained some of them. I'll explain them further with pictures. So this is, look at the two skiers. So this person now looks back and sees that other person has already passed from two sides at the same time. That's the concept of superposition. But something you see that this is from New Yorker in 1940. This is not too much after the quantum mechanics was developed. A particle can take two paths simultaneously if it is not observed in the interim. If you observe, you cannot see that there are two paths. Observation means it's a measurement, basically. When you do the measurement, the superposition collapses, and that's what you already know, right? So this is one idea that I explain it further. So you have two boxes. One is marked with 0, other one is with 1, and you have one electron. So superposition means that the same electron is at both the boxes simultaneously. The same electron, but it is in both the boxes. In terms of state, in state 0 and state 1. Then, if it is classical, then it cannot be simultaneously two boxes. It's either in this box or in that box. In quantum, they can be in a superposition state. So at the same time, they can be in both the boxes, both the states. So the electron is in superposition until it is measured, right? Now, say you want to find out actually by measurement where it is, in which box it actually is. So this process means it's an interaction with the measuring device and the particle, the quantum state of the particle. So as soon as this interaction happens, the superposition collapses into one of these states. So then you find it is either here or there after the measurement. But in which box you'll find it, you don't know. That's an intrinsically random process. Again, you can calculate some probabilities, but you cannot tell in which box it will end up. So this is very strange, but it is real in the sense that actually it happens. Otherwise, whatever you have been doing with quantum computation or whatever, it would not work. So we don't, even though we don't understand how this superposition happens, but it does happen. Right? So superposition, if you find difficulty in understanding or realizing how it happens and why it happens, and you are not the only one, even the biggest of the scientists, Einstein never believed in that. So the question is, do you really believe that the moon exists only when you look at it? Right? So he also said that the God does not play dice. Okay, when you play Ludo, you don't know, when it is rolling, you don't know in which state it is, but only when it lands, that means measurement has been done, then only you know what phase it has ended up with. So these two, of course, the quantum proponents are Niels Bohr, and this is Albert Einstein didn't believe that. So God does not play dice with the universe. And Niels Bohr says, Einstein, stop telling God what to do, because that's the way the nature is. So you cannot direct God to change the nature. You try to understand the nature, right? So that's what the duel between these groups. So now I give a little description of these two boxes that I mentioned. It's the two states, and the quantum particle is in a superposition between these two states, right? Find these two states. Think of that, say, even hydrogen atom, n equal to 1, n equal to 2, and others, right? So electrons can be at n equal to 1, n equal to 2, or any other states, depending on what the condition is. If the temperature is very high, you may find the electron most of the times in the upper level. If you take the spectrum from the sun, do an analysis, you get lines, right? And there you have Balmer series. It's a hydrogen transition from a high state to the lower state, right? So at that temperature, the electron occupies most of the times upper state. But you can have a condition, say low enough temperature or something, then the electrons will spend most of the times lower state. So you can confine this to two states, the ground state and the first excited state. So you can call these two states like 0 and 1, and a superposition of that you write in terms of alpha power times 0, beta times 1. Alpha square gives you the probability of finding it in the 0 state. Beta square gives you the probability of finding it in the 1 state, right? So this is your superposition state. Entanglement, that's even more strange. Now we are dealing with 2 electrons now, 2 particles. For one particle, this first box 0 and 1, this one. For the second particle, 0 and 1. So you may find it in a condition here where both the particles are in 0 and both the particles in 1. It's not either or, it's a superposition of these two again. Through the interaction, you can create such a state. They occupy like that. And let me try to use some analogy to explain this. So this flying eagle, see, say I call it, there are 2 quantum particles on this end and this end of the eagle. When they're down, I say they're at 0 state. When they're up, I call it 1 state, right? So eagle always flaps like this, right? It's either both of them 0 or both of them 1, right? So this is the superposition with this, between these 2 combinations, right? So it is the state is 0, 0 plus 1, 1, right? But when you do the mathematics of these things, you see something like this. This is a state. It's 0, 0, both of them are 0 or 1, 1. Divided by square root of 2, that gives you probability, right? 1 over square root of 2 square is half, half, equal probability. So this is also called the Bell state. It's an entangled state. So this is entangled, you can see they cannot be independent. If both of them are either 0 or 1 and the superposition. So they are entangled. Well, let's take another one. So this is a seesaw. And say this is one quantum particle, this is another. Again, you call it when it is down, it is 0. When it is up, it is 1. So in this condition, the first one is at 0, second one is at 1. When it goes other way, this one is 1, this one is 0. So this is entangled only in that way. It cannot go in any other way, right? So this is 0, 1 or 0. So this also has a mathematical description. What happened? Oh. Stuck. So your all mathematical description, Bell states you can get in picture. This is one Bell state. In other words, this is another Bell state. So in mathematics, you write it like this: the 0, 1 state plus 1, 0 divided by the square root of 2. So these are they're all entangled states. So superposition and entanglement, these 2 concepts again, Einstein, how Einstein had taken it. First one you have already seen. And the second one about entanglement said it's a spooky action at a distance. I didn't explain something for the eagle, say, for example, one quantum particle here, one here, right? Now imagine that this eagle extends over the whole universe. So at one end of the universe, this is one quantum particle, this is another, but they are entangled, we know that. In that case, if I measure just one of them, I don't have to measure the other one, I already know it. I know if it is 1 here, it is 1 here. I know if it is 0 here, this is also 0 here. Second case, if I know it is 0 here, I already know this is 1. If it is 1, I know it is 0. When it is entangled, you have 2 qubits, right? So that's why it's a spooky action at a distance. Now, in between, he mentioned something like about EPR paradox, Einstein-Podolsky-Rosen paradox. That was a thought experiment that Einstein and together with them, they proposed, but eventually, I mean, that failed. But Schrödinger, almost immediately after 1935, he had given this picture like Schrödinger's cat, it is called. Imagine I have a box, black box, and inside there is an atom, radioactive atom, and a cat. And you can't see anything in between. So you don't know the state of that. The cat can be in two states, alive and dead. It could be superposition of that. The atom can be in two states because either what is it? Decomposed, disintegrated. Yeah, either disintegrated or not. These are the two states, right? So we don't know. If you have not opened it, you don't know what happened. What is the state of this atom? Neither do you know the state of the cat. But this device builds up an interaction between them. That is, this is a detector, and this is a hammer mixed with that. This is a glass flask with poison. So now, when the atom has decayed, then this decay will be detected here, and then this will be released, and this will hit the glass jar. Poison will come and it will be dead. Right? But if the atom has not decayed, nothing will happen. The cat will be alive. So now, imagine that the lower part of the box is still closed, it's dark, but the upper part you can see. So now you see that if the atom has decayed, you know that the cat is dead. If the atom has not decayed, the cat is alive. So these are entangled states, right? You have to know only the state of one, you automatically know the state of the other. So superposition is the ability to simultaneously exist in multiple states, right? And entanglement is the ability to exhibit connection between particles despite large physical separation. It could be, as I said, two ends of the universe, right? So this is what it is. That means the entanglement contains superposition as well as correlation, right? These two bits are correlated. So entanglement, superposition, are they correct or not? Einstein questioned all these things. He ridiculed those. But eventually experiment showed that they are correct. And these three gentlemen got Nobel Prize because of that, using experiments with entanglement, right? And entanglement has uses not only in quantum computers, but also in quantum communication. Right? And one of these, Anton Zeilinger, they carried out some communication, quantum communication, using the entanglement process. This was in a place where it's called Canary Island. This is Europe, Portugal, this is Morocco, this is Canary Island within the Atlantic Ocean. So from one island to the other island, they sent a quantum bit. Quantum bit you cannot copy, as Professor Pati has mentioned, right? So if you cannot copy, you cannot send it. So this has been sent using the pair, that's the entangled pair that is also sent through that. So this is the experiment of Anton Zeilinger in 2012, about 150 kilometers away from this island to that island. They transported, the teleportation is called, using that. Now let us come back, not with those pictures. Now 0 or 1, say head or tail. If it is classical computers use transistors. A transistor can be either on or off. So say one state you can define as 0, the other state 1. So the either or, 0 or 1, right? But if it is quantum, then you know this 0 and 1, both of them, right? This is superposition, but if you have 2 or more than 2 quantum systems, you can have entanglement between them. Now let's talk about the computer, the basics of computer. Classical computer is, you know, transistor either 0 or 1. So I say you have a computer means you need many of these transistors, right? So these days, the most powerful computer has almost close to 1 trillion transistors. Definitely tens of billions, many of them. And even the iPhone 14 has 16 billion transistors in it. Okay. So if you have, say, 3 registers, each of them is a transistor. It can be either 0 or 1, right? Now, how many combinations can be there? 0, 0, 0, all the way to 1, 1, 1, 8 combinations, right? These 8 combinations means in terms of numbers, if you want to say 0, 0, 0 is 0 and 1, 1, 1 is 7. Think of that. Why did I write that? If you want to write 589, 5 is in the place of 100, 8 is in the place of tens, and this is place of unity, right? But here the base is 10, it's the decimal system. Here we have 0 and 1 only. It's a binary system. So it's 2 to the power 2 times 0, 2 to the power 1 times next one, 2 to the power 0 times that one. So this is 0 to 7. These are the 7 numbers that you can represent there. But at one moment, can it store all the 7, all the 8 numbers? No, because one transistor can be either 0 or 1. Next one, either 0 or 1. Next one, either 0 or 1. So it can only represent one of these 8 combinations at a given moment, right? But if you have a quantum bit here, quantum particle with 2 states, then they can be in superposition. So then all these 8 states can be in superposition. So you can store all the 8 numbers simultaneously. So this is the storage capacity goes up exponentially. 2 to the power 3. If I had 4 qubits, 2 to the power 4, 16 times, right? So if you have 100 qubits, you can calculate what the storage power goes up. So this is one, and this is another. How does it work? If you have, say, a maze here, and you leave a ladybug from here, it is trying to find the exit. What is it going to do? It is going to come explore here. All different possible paths it will explore one by one. But on the other hand, if you have a group of ants, ant colony, and lots of ants go simultaneously, they probe all paths in parallel. They can find the exit in very faster time. So the quantum computation is like that, and the first one is like classical computation. A Technical University Delft website has a simulation of that in animation. So the power increases exponentially in proportion to the number of qubits for quantum computers. And here power increases in 1:1 relationship with the number of qubits, right? So 1 trillion qubit, if you have for the most powerful classical computer, you know, can imagine with how many qubits you can attain that. Very small number. So let's, so this one you have already seen the power of. This was 53 qubits, and most powerful classical supercomputer even could not have done it in 10,000 years, that calculation. Okay. So now think about that, all the atoms in the universe, all the planets, all the stars, all galaxies together, they have how many atoms are there? If you take all these atoms and say you make a classical transistor, a classical computer, so then it would be something like 10 to the power 90 or something atoms. So that many transistors, you will build it, and if you build a quantum computer with 300 qubits, it would be more powerful compared to that. Okay. Now we have to know a little bit more about that presentation of the quantum state of the system. So this is done. This is the superposition we have explained. Now this is called the Bloch sphere. A quantum state is represented on that. The vertical vector here from 0 to this point, North Pole, is called 0 state. And this is 1 state, right? And any other point, if you make a vector ending up at any other point on the surface of this Bloch sphere, is a superposition state between this 0 and 2. And you know that how it is written with respect to this axis. This angle is 0, theta is cos theta by 2, and one component is sin theta by 2, and there is an angle from with x-axis, this vector, that is phi, e to the power I phi. So alpha and beta, when I said it was a complex, in general, they're complex. The complexity you can see here, it will be power I phi, right? But when you get the probability, complexity goes away. You get only the real numbers. Okay. Now, important thing is that, I'll explain that, classical computation and quantum computation, what's the difference in that? Classical gates are there, you know that when you make a circuit, say adder circuit, there are classical gates, right? Similarly, for quantum computation, there are quantum gates. What do the gates do? They basically take this vector that you have shown here, and it can place it anywhere on the surface of this Bloch sphere. And as long as you put number of gates, it will do that according to what gate you use. So it will never collapse from the superposition. But finally, when you measure, make the measurement, then it will collapse to 0 or 1. Okay. So these are two circuits, the classical. It's a full adder circuit with the classical gates and the full adder circuit with quantum gates. So here, if you look at any position, you can find what's its value, 0 or 1, right? One of them. But in this case, for all these gates here, you cannot tell whether it's 0 or 1. You have no idea, it's in superposition, right? So you don't understand what really it is in the superposition state. But then what this shows, this is a measurement. When you have measured it, it collapses into 0 or 1. So end results that you get by measurement. So now, as I said, that just one measurement will not do because it's probabilistic. To get this 0, say if we make 1,000 measurements, right? And 900 times, 990 times it is 0, and 10 times it is 1. So now you know that it is 0 actually. So that's how you have to carry out your calculation. How does one implement a physical qubit? These are just logic ideas, all these things I mentioned, right? So physically, a quantum computer has to be there and something you have to do with that to get the calculation. If you just write on the paper, it will not do anything. So how do you implement a physical qubit? What is that physical entity? That will be a qubit, right? That's an important thing that you have to answer. So there are various quantum systems that can be utilized as qubits. Just to give you an impression of that, the left column, it says sub-nanometer system. These are very small systems. Size is smaller than a nanometer. Could be electron, it could be a proton, it could be an atom. All these things. Here is the picture of an atom, as I explained for hydrogen. Or there could be some other atoms where you can select actually 2 states. So they will be confined within these 2 states. You can have that as a qubit. Second one is a nanometer scale size. So you can have an aggregation of atoms. Say 100 atoms clustered together. So what will happen? The electron cannot come out of that, right? So what you can represent this as a potential barrier at the surface of that, right? So it's a particle in a box that you have studied in quantum mechanics, right? So that means there the electronic states will be discrete and confined like that, right? So you can use a quantum dot, this is called quantum dot, to implement your qubit. Or you can take a large material that is like a superconductor. Superconducting material itself is a quantum system. And using that, you can generate something, an artificial atom, that will give you 2 states, a quantum bit with that. Obviously, I'm not going to explain the other things now because just I take one example of that. Say superconducting qubits, how do you make that? So we can make special electronic circuits with superconducting materials, and that will behave like a system with discrete energy levels like an atom. So how do you make a quantum computer using a superconductor? You have to make an LC circuit. In electronics lab, you know, you have built an LC circuit, right? So that's what you have to do using superconducting material in LC circuit. And LC circuit is what? It's a simple quantum oscillator, right? In first year undergraduate, you have done simple harmonic oscillator, and it doesn't have to move like that. LC circuit also, the charge oscillates like that, charging, discharging, right? So this is also a simple harmonic oscillator. So it has a certain frequency, and the frequency is given by omega equal to 1 over square root of LC. And what you want is a quantum harmonic oscillator with discrete energy states, right? So if your L and C are very large, that we pick up from your electronics lab, you'll find the omega value is very small. So energy spacing would be so small, it's like a continuum. So that's not a quantum. You have to choose values of L and C small enough so that omega is large enough, so the energy separation is large. That's where it would be quantum. So you have to build a quantum oscillator. And then we can choose the lowest two states of this harmonic oscillator to represent a qubit. So why superconducting material? Is that you know that superconducting material has zero energy loss, or it has resistance is zero, right? So if you have a superconducting ring, you set in a current, it can flow forever. The current can flow for 100,000 years. It will not decay. R is zero, so I square R, the power loss is zero, right? So here in this system also, you don't want any power loss from this. And so now say we have built this LC circuit, and this is my harmonic oscillator. Energy levels are discrete, right? So these conditions are fulfilled now, right? But there is a problem with this picture, this equal spacing of energy. I'll come to that later. But let me tell you that problem is avoided by making this potential well, it's not harmonic, it's anharmonic like this. And then the energy level spacing should be different. So how do you make it anharmonic here? You replace this inductor, L, which is a linear one, by a nonlinear inductor, which you can make by implementing a Josephson junction. So here you see that the L is replaced by Josephson junction. So I have to tell you what a Josephson junction is before we proceed further. So what is a Josephson junction? It is actually two pieces of superconductor separated by a piece of insulator. And the insulator is very thin, it's about 2 nanometer. You have two superconducting pieces. In between, you have a thin insulator. So now in superconductor, what are the carriers? Cooper pairs, right? Not single electrons. It's a pair of electrons, Cooper pair. So Cooper pairs can tunnel through this insulating material and go from one side to the other. And this is a Josephson junction. And this provides a nonlinear inductance. You will not understand it immediately because you have to go to the mathematics of that to understand that it gives you the nonlinear L. So that's what you do. Now, current can flow through that, as I said. So let's pose a question that you have a copper wire connected with the circuit, and if there is a break in the copper wire, can current flow through this? You're wrong and right both. If the gap is large, it cannot. If the gap is small, it can. It's the quantum tunneling that takes place, right? This is by quantum mechanical behavior, this one. You have all studied that. Whoever have done quantum mechanics and quantum tunneling, you have studied that, right? So this means this side is this part, and this side is this part, and this is the potential barrier that is provided by the insulating material. So the electron tunnel from this side to this side through this barrier, right? So it happens, and the scanning tunneling microscope works on this principle that electrons tunnel from one to the other. So similarly, Cooper pairs can tunnel through that structure that I showed. Now I come back to this, why this simple harmonic oscillator things will not work, because if you want to know the state of the qubit, whether it's 0 or 1, when you finally make a measurement or whatever, then I have to interact with it, right? Without interaction, I cannot. find out. So how do I interact in this case? We interact with by sending photons with a frequency that corresponds to this energy difference between these two levels. Now imagine if I have harmonic potential, then all the energy separations are same. So they say I want to excite the system from 0 state to 1 state. I send a photon there, right? But it can also excite from 1 to 2, which is unwanted. Because with my qubit, I want to want with only with 0 and 1 state. So now if I have an harmonic potential, then you see this energy difference is smaller than this, right? So this photon can excite from here to here, but not from here to here. Just to avoid that, we need this anharmonic potential, right? And the Josephson junction is crucial for that, which is also made with superconductor. Okay. Now, even if you have made this, and we have not interacted with this microwave photon, right? But if I leave it at this temperature, room temperature, there's lots of thermal energy it's going to have, right? So this electron can occupy almost all the states with almost equal probability. So it is not quantum anymore. It's classical, right? I have to ensure that I am stuck with the lowest or the first one, right? And to do that, I have to dip it into a deep fridge to make it cooler. As I told you, for the hydrogen atom, if it is in the sun, they occupy n equal to 5, 6, 7 states, right? So, but if I cool it down, it won't occupy that much. But if I otherwise also say, if you put hydrogen in a tube light, discharge tube, right? But because of this high voltage, you can also see all those spectral lines, Balmer series, right? That means the electrons are excited to a higher energy level. So by cooling down, we ensure that our state remains occupied only at the lowest one. Then by sending the photon, I can excite it to 1. I can manipulate it, I can do whatever I want to do. So this is the cool. This is called the dilution refrigerator. Outside temperature is 300 Kelvin, the room temperature. But at different stages, the temperature goes down and down. At this here is 10 millikelvin. How much is that? Absolute zero is minus 273.15 degree. And 10 millikelvin is minus 273.14 degree. 0.01 degree above absolute zero. By placing your qubits or the quantum processor at that temperature, you ensure that it will behave like a qubit and you will be able to manipulate, or the gate operation you can do on that. So this is the dilution refrigerator that was seen. Now it is covered. You cannot maintain that temperature in air. It has to be under vacuum. So this is the enclosure there, right? So this is one of the dilution refrigerator, the quantum computers at IBM. And this is the one smaller version in our lab here, dilution refrigerator. So inside view was that, whatever I showed earlier. Okay. And these are the electronics that you have to manipulate or operate the gates on the qubit by sending signals to it. Okay, this one we have shown. And this, after that, we integrated lots of electronics within this. That you need lots of electronics that work at cold temperature. If you take any electronic component from the lab, it will not work at that temperature. That's a low temperature electronic components. And then here, now you see this cylinder. This cylinder is a magnetic shielding around the qubit because the magnetic field can disturb it. So the qubit is actually inside that. This is sitting inside that. And if you want to have a look inside of this one, this is like this. This is cavity holes within this material. And at the center of that, this little piece here, at the center of that is the qubit actually. That's the qubit. And this is where the Josephson junction is, in the middle of that. Let's say if you 20 nanometers or something is the size of the junction. That one. And actual junction is this, you have to blow up. This is made by lithography. Otherwise, you cannot make this small structure. Right? And this is the circuit. This is the Josephson junction and LC circuit. Okay, this one. And this is an oscillator circuit. It's an electromagnetic wave. That's a microwave that goes. It forms a standing wave in that cavity. So that circuit frequency has to match with this one, whatever you are sending. And through that, we can read the state of the qubit through that interaction. So that's with the cylinder, it is inside, and this is after putting 4 layers of clothes around it, and you see the outside there. So that's the electronics that you need to control, and this control goes through the top connectors to the qubit. Now, why quantum computers are so important? Imagine that at the outbreak of COVID, within 1 month, if we got the vaccine, how many lives could have been saved, right? But we could not. But quantum computers gives you that promise that they will do that someday. Because this year in the drug discovery, new drug discovery, what you do now, you just go to the lab and try out tens of thousands of molecules. Which one would be the right one for this, right? But quantum computers will be able to simulate many of these molecules, their properties, and they will tell you that you don't have to try so many. Just try 50 of them instead of tens of thousands. So within this 50, you will get your solution. So instead of spending 6-7 years, you may get the solution within a few months, right? So your drug discovery would be very accelerated. You'll discover new drugs pretty soon. And already the present-day quantum computers, which are not very big, you can do the protein folding, how the proteins are going to fold. And that's the molecular calculation. That's where you are going to need it for drug design. This is one. You can also, this is not only the drug, you can actually manipulate things. Like if you want, say, a material that is transparent like glass, but it is hard like steel. You can just now think of it, right? But if you go to the laboratory and try to find something like that, it may take years, not years, maybe centuries. And even that you may not find it. But now, quantum computer will allow you to simulate the properties of materials, and then they will tell you, yeah, you try this few materials. So you may find your solution. And someday, room temperature superconductors, for example, you may find such robust that you may fill the whole world with solar cells. You don't need any other form of energy, right? So these are the possibilities with quantum computers. And also climate change. The carbon dioxide is a big problem, right? The catalysis in this case, converting bad things into good ones like hydrogen. How we can do that very effectively, that you can simulate those properties using quantum computers. So climate change would be a big contribution for that. Then traffic optimization. Therefore, in Kolkata, you want to go from here to Howrah, right? So how long it will take, you don't know how to go. But so is the petrol consumption. And it's also, if you consume more petrol, it also adds to the climate. Bad climate gives you bad climate, right? So if you can to find how to optimize the route, taking all variables into consideration, then it is better for you. You can save money, you can cause less pollution, you can save time, all these things. So this sort of optimization problems, not only traffic optimization, in financial market, if you want to know which one you have to, where you have to invest, and that they can tell you that which one. It's portfolio optimization, that's called. Cyber and information security. quantum communication, as you mentioned, right? The cyber security means when you get a message now in WhatsApp or somewhere, you see it written at the bottom is 128-bit encrypted. So that other than you, nobody else can read it, right? But it may not last too long. It said the US National Institute of Standards and Technology has already said that quantum computers will be able to crack the existing public key infrastructures like 128-bit AES encryption by 2029. So if someone has a quantum computer, by that they will crack your message and it will not remain any secret anymore. So these are various possibilities with quantum computers. Now let us tell you where we are in terms of quantum computing. Let's look at classical computer, how it developed. It's 1906, this bulb, not the transistor, solid transistor, the vacuum tubes. But it took about, say, 40 years, and they developed this huge computer called ENIAC. It filled several rooms like that, like this one. Still, it could do very little. Then in 1947, transistor was invented. Just one transistor of the size like 1 centimeter by 1 centimeter. Now within 1 inch by 1 inch, you can have billions of transistors. The development went to that state, right? So let's see. Here, this is something, say it's the 2017. It's about 32 cores and about 20 billion transistors within that computer. And now it has reached almost close to 1 trillion transistors in that. But could you imagine your Facebook in 1950s, 60s? No. 70s? No. But the classical computers have started developing long back. It took so many years to do that. And quantum computation, or the quantum computers, this is idea was given in 1981, but say this 5-qubit quantum computer, the small one, was built in 2016 by IBM. 2016, right? So how many years now from there? 7, 8 years, right? Now it has reached up to 1,000 qubits or something like that. So it will take time, right? So we should keep hope that someday we are going to achieve all those things. So we have to be prepared. We have to be quantum. Right away, we have to start thinking quantum. And we have to get ourselves familiarized with this. Then eventually we'll get there. So let's look at this. The present day available computer. This was the Google Sycamore. This was Rigetti. It's also superconducting quantum computer. IonQ is a ion qubit, trapped ion qubit. This is IOP quantum. This one is D-Wave. This is also a big computer. This again superconducting qubits. Now, with all these developments where we are, you look at this picture in the middle and imagine what this is. This is not a grasshopper. This is the Wright brothers plane. So when you compare today's plane with Wright brothers plane, so for quantum computing, we are still at the Wright brothers plane level. We have a long way to go. But Wright brothers also had hope, right? Someday it will be a good flying machine. So someday we'll have flying quantum computer. That flying means within code. So let's keep our hope alive and get ourselves prepared to go ahead. So thank you for your attention. These are the people who worked actually. Dr. Snehal Mandal is there, the postdoc, Biplab, and Ayan. They're the PhD students. They're the one who are building it. Okay, thank you. You're free to ask questions, and no questions are dumb questions. Yeah.
So when you show that ladybug, that one,
Yeah.
so it is trying to find different possibilities. But how this quantum computing, like you have two options, right?
Now, but other one is that I sent many ants there, and each of them is exploring different direction. And finally, the one accidentally also will go to the right way, right? Then I already get the information, my result.
So
So what I said with the classical computer and quantum computer with 3 qubits, with 3 bits and 3 qubits. With 3 bits, you have only one choice.
okay.
But with 3 qubits, you have superposition of 8 states.
Mhm.
So 8 states are working together for you. So this is the ant colony.
Mhm.
The other one is the ladybug.
Okay.
Computers, you give the list, the quantum computers, but how many of them are based on the superconducting qubits? Because there are
IBM, then Google, D-Wave in Canada, Rigetti, these are all superconducting based.
so as of now, it is the superconducting ones which have established itself as the main this thing, or because there are so many other.
I would say it's one of the forerunner. I didn't add one slide there. So that showed, I mean, the two axes. One is here, this gate speed, how long you need to operate a gate. And other one is the coherence time, how long this qubit remains good. On the way, if it interacts with something, then it's vanished. It collapses into something, right? How long? This is called the coherence time. And say if you have a coherence time of 100 milliseconds, but if you have a gate operation about say 100 nanoseconds, there's still 10 to the power 6 operations you can carry out when the qubit is good. But if your gate time is longer, millisecond, then you can operate only a few gate operations. After that, the qubit will not be good anymore. So in these two, there are two occurs. The superconducting quantum bit has a very high gate speed. So coherence time is not that great, but trapped ion has a high coherence time, but also low gate speed. So these two are trying to approach, say if I show something like this, approach this corner, high speed and high coherence time. So they are trying to approach from there. And in the middle of that, cold atom qubits are also trying to get ahead. So eventually, which one will win, we don't know. But right now, the most dominant ones are superconducting qubits. And most of these examples that we gave are superconducting qubits.
And you made a passing phase remark regarding the high temperature superconductors, if at all, or when it will come. So do you think that, I mean, assuming that I mean, the way things are going, it is not impossible that we will get near room temperature superconductors.
Yeah,
I mean, all the arguments that you gave, the 0 and 1 thing, so will it be possible that we don't operate at the the ultra low temperature?
No. If you want to make computer, then you have to. But I gave that comment at the end regarding the materials. Quantum computers' contribution to the drug discovery and the new material. You can actually manipulate even the biological systems or materials or chemistry, right? So that you can project, I mean, at what condition things will be like that. Superconductor. Appropriate one that you can use for, say, an example I have given, that electrify the whole world with very little loss. Someday, because it will contribute to the material.
Yeah, sure. Thank you.
Thank you, Professor Dev. I would now request Professor Das to give everyone an overview of activities that are carried out in Secure.
Yeah, I think this is that's fine. I mean, I'll remain Indian. So, okay, so thank you. Okay, right. So I'll just give you an idea of what kind of research we're doing, and then you'll see a video. I think we have a 5-minute video that describes our activities. So as we have been, discussing the three main areas that we're working on. One is quantum computing. You just got a talk on quantum computing. And so what we're trying to do there is to actually build a quantum computer. It's obviously very challenging, but that's what we're trying to do. And Professor Bhupen Deb is leading that activity of building a quantum computer using superconducting qubits. Now, we actually plan to do two kinds of quantum computer. So the quantum computer he was talking about has qubits and gates. There's another kind of quantum computer which only has qubits, and that's called a quantum annealer. So our plan is to do both. A gate-based superconducting quantum computer, and also a quantum annealer using just superconducting qubits. And so we have one postdoctoral fellow and 2 PhD students working on that project. Now, in quantum computing, we also have a theory group where that's a fairly big group. There are 3 faculty members, and we have about I think 6 students and a few postdocs. And what we do is we define a particular problem. It could be, I was just talking to you about working on molecules, atoms. So we try to compute properties of atoms and molecules using a quantum computer, the kind that Professor Deb talked about, but something that has already been built. Like, IBM has built a quantum computer. There are other companies. There's a company called Rigetti. So we use, there are trapped ion quantum computers. So we have access to some of these quantum computers. Using those quantum computers, we calculate properties of atoms and molecules. And we have plans of doing other things as well. So for that, you have to define an algorithm, that is a method of calculation. And then you need a quantum computer. And then using your algorithm and a quantum computer, we do quantum computations. So that is one area of research. And we also have a faculty member who works on quantum machine learning. So this is Dr. Shivdas Roy. So basically, machine learning is something which many of you are familiar with. But so if you use machine learning on a quantum computer, that is, if you have a suitable algorithm for doing machine learning on a quantum computer, so that is quantum machine learning. So that is about quantum computing. And fairly recently, we have started activities in quantum communication. So Professor Arun Pati and Professor Pankaj Agarwal, they're working on quantum communication and more generally on quantum information. So as you might have gathered, quantum information covers everything: quantum computing, quantum communication, quantum sensing. So So that is in theory. And quantum sensing, we have two experimentalists, Dr. Tanmay Basu and Dr. Aishik Acharya, who've been working on quantum sensing. Now, basically, the idea is, sensors can measure time, they can, measure magnetic fields, or gravitational fields, electric fields. So quantum sensors will be much more accurate, much more sensitive than regular classical sensors. And so that's another activity that we're involved in. So these three are the broad areas that we're working on. And to that, I would also add quantum materials, as you probably gathered from Professor Bhupendev's talk. The qubits that are used in a superconducting quantum computer, that needs a material and with the qubits. And so we still don't know what is the best material. For example, if you take a superconducting quantum computer, we do not know what would be the best material for qubits. So there is work going on there. So that area is called quantum materials. And so we are working on that as well. In fact, in some sense, we began our activity by looking at quantum materials. So now we will be part of the National Quantum Mission, which was announced earlier this year. And we have applied to work on various projects involving all these areas: quantum computing, quantum communication, quantum sensing. So broadly speaking, these are the areas that we're working on. And of course, as was mentioned in the inaugural talk, we also have a PhD program. The PhD program currently is in collaboration with CSIR. CSIR has an academy called ACSIR, and they can give PhD degrees. We also have a collaborative program with IIT Tirupati. And as was mentioned earlier, we will be becoming a university starting next year. So then we'll be giving our own PhD degrees. And we also have collaborations, because this is an area where you need to collaborate with groups, not just in India, but outside of India as well. So we have collaborations with a number of groups outside of India as well. For instance, those of us who are doing quantum computing need a quantum computer. Now we are building a quantum computer, so when that becomes ready, we'll use it. But for the time being, we are using commercially available quantum computers, like from IBM and other companies. And we're also using quantum computers that are built in universities outside of India. So this way we've been able to make some progress in the field. So this broadly is what we've been doing for the past few years. Now we'll show you a video. Now the American Physical Society had made a video on our activities, and that is available on YouTube, but we'll show it to you now. So this video is about our activities. So maybe I can give you the link and you can see that later as well. The Center for Quantum Engineering Research and Education, or SECURE, was established in 2020. The objectives of the center are twofold. First, to pursue cutting-edge research in quantum science and technology. And second, to provide high-quality education to students and to train them to carry out the Center for Quantum Engineering Research. Our first The Center for Quantum Engineering Research and Education, or SECURE, was established in 2020. The objectives of the center are twofold. First, to pursue cutting-edge research in quantum science and technology. And second, to provide high-quality education to students and to train them to carry out research in this important area in the future. The primary research area that has been pursued in SECURE at the moment is quantum computing. We've made substantial progress in the applications of quantum algorithms to atoms and molecules.
In our group, we focus on carrying out atomic and molecular calculations on quantum computers using quantum algorithms. Having said that, we also focus on allied areas like quantum error correction, and most importantly, we are also focusing on our long-term goals of tackling real-world problems using quantum algorithms.
So if the technology moves in a direction such that the error mitigations are more controllable, number of qubits much more, and the decoherence time is controlled, then there are lots of possibilities. I don't foresee immediately emergence of tabletop or laptop computers in the quantum domain, but it will certainly come in a way. I mean, who could foresee that PCs will be developed?
Quantum systems with which one performs quantum computing are fragile. They are subjected to errors that we do not have control over. The theory of quantum error correction allows one to overcome these errors by storing the quantum information of the quantum system into multiple quantum systems non-locally.
We are building a novel quantum machine learning model that mimics quantum mechanical state evolution so that it can be self-aware to be able to correct its course if it can go wrong, unlike any existing machine learning model.
I have been working in the field of quantum computing, quantum information science almost for last 34 to 35 years. I am the first person to start to initiate this field in India. The recent topics that I have been interested in over last 5 years or so is to do with quantum speed limit and its applications in quantum adiabatic algorithm and quantum algorithm SECURE at TCG Quest. Really one of the prime center that has been initiated over the last two years or so. We can discuss with experimental people and then try to implement your idea and they can test it.
We plan to implement the superconducting qubit platform for both gate-based and annealing-based quantum computation. For qubits, it is desirable to have longer coherence time for all applications in quantum systems, including quantum computation.
In quantum integrated circuits, electrical signals must flow without energy dissipation. So the materials used for building the circuits must have zero resistance at the operating temperature and the transition frequency of the qubits. Low temperature superconductors are thus a perfect candidate for this job.
Scalability and stability are the two main challenges in present quantum technology. At SECURE, we are planning to overcome these problems by implementing chip-scale architectures using silicon and lithium niobate platforms.
We are also focused on translation research, where we can bring the science from laboratory to the field applications. For this, we have working on the quantum sensing area, where we will develop the cold atom gravimeter where we'll map the gravity locally.
The coursework is a perfect blend of components from quantum computing, where we learn different algorithms like the quantum phase estimation and the variational quantum algorithms.
Here, I've been exposed to many talks from different scientists in various aspects of theoretical and experimental quantum computing. And also, I feel like I'm able to think more creatively than I used to do, because I've been working in collaboration with different people, which is something that is not very common in Cameroon.
The installation of our first qubit is an important milestone in our quest to build a full-fledged quantum computer, which would be invaluable for both basic and translational research.
Okay, so with this, we conclude our series of talks for today. I would like to extend my thanks to all the speakers, the professors, as well as the audience. I would also like to thank the organizers, without which this small celebration would not have been possible. They are Tanmay and Prasenjit. They're sitting in the last row. And now what we have is a short snacks break, after which there will be a tour of the experimental labs. So we shall all meet there again. Thank you.